concentration is on braid theory. The questions we will answer in this presentation are: what is a braid? How to represent braids algebraically? What are the basic elements of braids? What are basic elements? How do you undo or find inverses of braids? And is there a braid version of the knot theory's Rademeister groups? So what is a braid? A braid is a tangle of n strings that are not connected to one another. Formally, Bn denotes a set of all braids with n number of strands, where n is a positive whole number. And here are some examples of braids. Where it has two strands. B3 with 3 strands. And you also have the trivial braid, which is just any number of strands that aren't crossing another. And that's the trivial. And Hungie will now talk about basic elements.
Okay, so there are basic elements in braid theory, basic elements are formally called generators. And we've hypothesized that every braid could be built off of these basic elements. So for different braid groups, for different ends of Bn, there are different basic elements. So the first group we looked at was B2, because it's the simplest braid that's out there. When we looked at B2, we discovered that this was the simplest braid, where we have one string crossing its adjacent string only once. So this is a basic element. Now some of you guys might realize that this also meets the condition of only having one string cross its adjacent string. But this braid is the inverse of this braid, and we'll talk more about inverses later, but the basic thing is that we will not count this as a basic element. And so we looked furthermore, so like at B3. And in B3, we still want only one strand crossing its adjacent strand. So we'll have this, and we'll have a trivial braid here. Now there are two places where you can put the trivial braid. One is like this, and the other will be like this. And so you can see that there are two basic elements here. And this pattern continues as the braid group increases. And so we got that for the group Bn, there will be n minus 1 basic elements because of the fact that there are n minus 1 pairs of adjacent strings. And since our goal in having this is to find a way that we can write this algebraically, we denote these crossings as sigma sub I. And something happened with our PowerPoint, so it's not sub anymore, but it's supposed to be. And so we have it, so then the sigma sub I is equal to the braid that is equal to the basic element, where the ith plus first strand crosses the ith strand. And so when we can have like a braid such as where this is sigma sub 1 and this is sigma sub 2. And so this braid is equal to this algebraic representation. So multiplication of sigmas from left to right is equal to the diagram from top to bottom. And inverses.
Okay, inverses of braids. The inverse of a braid undoes itself. And the way you denote an inverse is sigma sub I minus, sigma sub I inverse, yeah. Where the ith strand crosses over I plus the first strand, which uncrosses sigma I. So now we need to find out how to find the inverse of any braid. So if you have sigma 2, which is this, sigma 2, and you take the inverse of sigma 2, which is this, and multiply them, and by multiplying you just stack it on top. You can take this strand and pull it over the other strand, and you will get the trivial braid. And so, since every braid has an inverse, and every braid is made up of sigmas, you can just undo each sigma, each one by multiplying it by its inverse until we get 1, which is equal to the trivial braid.
Okay, so in our class, we learned about Reidemeister moves and knot theory, and they are shown on the PowerPoint. And so we wanted to see if we could rearrange braids in a similar way that Reidemeister moves rearrange knots. So we tried to look for moves that were kind of based off of these Reidemeister moves. So we looked at the first move, and it's where there's a line, and then there's a strand, and the strand kinks up itself. Well, in braid theory, we can't have kinks. So the first Reidemeister move does not apply at all to braid theory. Now the second Reidemeister move, it's where there are two strands, and then one strand overlaps each other. Now, if we can see, there are two crossings there, and it would be sigma k times sigma k inverse. And as Annie showed, then sigma k times sigma k inverse is equal to the trivial braid. So yes, the second Reidemeister move does apply in a similar manner to braid theory. Now, in the third Reidemeister move, we saw that there was a crossing with a third unrelated string lying on top of it. And we can move that third string above the crossing or below the crossing. In a similar way, we can have a braid that looks like this. And we can see here that this strand right here does not actually interfere with this crossing. So we could also move it to be like this. And it would be the same braid. We have another move in braid theory that is not related to the Reidemeister moves. And this is for braids that have more than 3 strands. So let's say we have 4 strands, and we have them crossing